the difference between science and medicine is, for medicine, the consequence could like kill the patient, because the patient does not have knowledge of what is going on. But with science, I can only influence people who understand it. If they don't understand, this one doesn't exist. So I don't care to talk to people. It's not like commercials, but this thing can only be communicated to people who understand. When they understand, they will know what is right and what is wrong. So I don't have a possibility to poison them. So then, and there was another thing. I thought I would probably send him a mail saying that because he said impossible, and I said impossible is nothing. If I give you the paper, just read it. Then you see yourself.
I tell that to my students all the time.
You have to get your own judgment. Yeah, that's my talk. Thank you very much.
Yeah, question. You're associating the electron charge with the twist, or you say the electron charge square.
It's square, actually it's square.
Obviously that leads to the question, well, how is the electric field associated with this topology?
Yeah, I'm working on that. I know how to work. I know how to work on it.
Right. What's your direction on that? It's a question then.
Well, because let's start with this, the mathematics of these space curves. But Gauss worked on this space curve in higher dimension. He has Gauss integral high dimensions. But there was like more comprehensive work was done by somebody from UC Los Angeles in the 60s. I think George White, his name. That's a pretty long paper. It was also pretty difficult to digest. And then there was a shorter, concise version, where let me see if I get everything right. Just I think it's quite familiar. So first of all, you define the twist, and then you have but the motivation for this is on page 451. So what you have a what he defined as Rayleigh number, and it's connected to Lincoln number and a twist number. So the twist number is defined as the twist divided by 2 pi. What it does is, if you have a strip, like a piece of paper, it's very simple. So yeah, this one is flat, there's no twist. So if you turn it like 2 pi, and then you get a twist. But then you divide it by 2 pi, you get twist number 1. So, and you can do any other ways, like you get more twist numbers or less twist numbers. And then in a way, the twist is kind of quantized, because you cannot get something in between. And then there's a Lincoln number and Rayleigh number he defined. And his work was more concerned with the biological subject, which is the supercoils of the DNAs. And then Francis Crick saw this paper. He wrote a kind of abridged version, saying, well, I think it's more or less that after Francis Crick's paper, every average biologist should be able to understand this. That was in I think the 67 or 69. It's on the reference list. So then because of the dimensional things and everything, but so this one is associated with charge square, not charge. That's something interesting. I saw George has a book upstairs. It's the physicist's conception of nature. That's the thick one dedicated to Dirac. There, Dirac has a paper. He was discussing about the fine structure constant, which is E squared divided by h bar c. And he said, well, this one is dimensionless, and this one is charge square, and this one. And well, what he was talking about is, do we believe, let's see, well, if we do it the other way, so it will be alpha times h bar c like this. So now the question is, if this thing is fundamental, well, why it involved a square root? That's, you will have it directly. You cannot start a square root and then go to the square, because this thing will be very sort of uncomfortable in a way. So that is there has something you probably have to start think this one as an entity rather than this one. But I don't understand myself, because in our classical electrodynamics, what we always measure, we are claiming this one is more elementary than this one. But in quantum electrodynamics, actually your expansion parameter is actually this one. You don't really have charge. You have charge squared as kind of fundamental entity. When we do the renormalization, it is charge squared. It's not charge itself.
Well, the same is true in classical mechanics, because what we actually measure is the force.
Yes.
So you could say, okay, it's a field times the charge, but the field itself is proportional to the charge of the source.
Yeah, right. Yeah. So that's also interesting. Say if we have our Coulomb law here, well, this is the force, and then the potential will be still E squared. It will be R. So either one you want to put negative sign, which will be connected with the simple connection. But it's kind of difficult to conceive, to perceive. So if you have one charge here, one charge there, and you say, well, this guy produces a field, if we don't care about this one, and you say, well, this is my test charge. The definition of the test charge is to say this one does not influence the distribution of this field. It only maps how large this field is without influencing this one. So then you move this around, and afterwards you get this one. But what happens if you say, well, I don't have a test charge? Well, how do you get charge squared in that case? Without just arguing for the dimensions, which would be, these things will combine give you the force. But we skip the constants and the units.
Okay, well, the time is moving on.
Yep.
We've got two more speakers. So thank you very much.
Thank you very much.